You know, when you think about it, the flicker of a tiny candle and the massive roar of a rocket engine have something incredible in common. What if I told you they're both governed by the exact same fundamental principle? Well, today, we're going to pull back the curtain on that principle. We're diving into something called thermochemical equilibrium, the key that lets us predict the final outcome of some of the most powerful reactions in the universe.
So, let's start with a really simple question. What actually happens when something burns? I mean, we all see the flames, we feel the heat, but deep down, at a molecular level, there's this incredibly complex chemical dance going on. And the amazing part, this seemingly chaotic, wild process, it actually has a very predictable, very stable endpoint.
To really understand something like combustion, we have to look past the flames. We need to start asking the right questions, the critical questions, like what new stuff is actually being created in that fire? How much energy is getting blasted out? And what's the final temperature of that flame? These are the exact questions that engineers and scientists have to solve every single day.
And look, these aren't just academic questions for a science quiz. Knowing the answers is absolutely crucial. If you're designing a power plant or, say, a brand new rocket engine, you have to know what new molecules are going to form, how much energy you're going to get, and how hot it's going to be. The ability to predict the outcome of a reaction, well, that's what really drives innovation.
So how do we answer all of these questions? Well, luckily, there's one single, powerful concept that gives us the key to all of them. And that's this idea of thermochemical equilibrium. It's the tool, the method we use to figure out the final settled state of any chemical reaction.
Okay, the best way to think about this is to imagine a ball rolling down a bumpy hill. Where does it end up? It always settles in the lowest valley, right? That's its most stable point, where it has the least amount of energy. Thermochemical equilibrium is exactly that, but for chemistry. It's the most stable, lowest energy state that a bunch of chemicals naturally want to settle into after a reaction is all said and done. It is literally the reaction's final destination.
So let's break that down. Before the reaction, over here on the left, you've got your starting lineup, your fuel, your oxidizer, and it's just brimming with potential energy. Then the reaction happens, and afterwards, over on the right, you've got a completely new mix of super stable molecules, things like carbon dioxide and water. That huge drop in energy from before to after, that's what we see and feel as heat and light. And the real power here is that we can use equilibrium calculations to predict exactly what that final mix is going to be.
So how do we actually find this final state? Is it just guesswork? Nope, not at all. It's not trial and error. Instead, we use a really powerful calculation method that lets us figure out the precise outcome before the reaction even kicks off. All right, so here's the sciencey term. It's called Gibbs free energy minimization. Now, I know that sounds complicated, but the idea behind it is incredibly simple. Just like that ball rolling down the hill, chemical systems are always trying to get to their lowest possible energy state. It's a fundamental rule of nature. This calculation just lets us find that most stable, lowest energy configuration for them.
The whole process basically boils down to a clear four-step recipe. First, you figure out every single possible chemical product that could be made from your starting ingredients. Then, the heavy lifting. You calculate the Gibbs free energy, that energy level, for every single one of those possible combinations. After that, you just have to find the one single combination that has the absolute rock-bottom lowest energy value. And that's it. That lowest energy mix is your final state. That's equilibrium.
Okay, so we've got the how, now for the really fun part, the why. Why does this all matter? Well, this calculation is so much more than a theoretical exercise. It's actually a cornerstone of modern technology, and it unlocks a huge world of real-world applications. Let's start with a big one, rocketry. Engineers rely on these calculations constantly to design and perfect advanced propellants. By predicting the final temperature, the pressure, and exactly what's in those exhaust gases, they can figure out the thrust and efficiency of a rocket engine before they even build a single part. And this goes for everything from old-school solid fuels to really cutting-edge stuff like gelled hypergolic propellants.
But it's not all about fire and explosions. Here's where it gets really surprising. In materials science, they use the exact same principle to create new metal alloys. By calculating the stability of different molecular arrangements in supercooled liquid metals, scientists can predict what the final structure is going to look like when it solidifies. This lets them basically design alloys from the ground up to have specific properties like being super strong or incredibly lightweight.
This same idea is also absolutely vital for building a more sustainable future. Take green energy.
Researchers use these calculations to optimize how we burn biofuels, like biopellets, or even agricultural waste, like coconut husks. By figuring out how to squeeze every last drop of energy from these renewable sources, we can cut down our reliance on fossil fuels. It's a huge deal.
I mean, just look at this list. The versatility of this one tool is just mind-blowing. It's used to analyze alcohol-based propellants, to study high-energy fuels rich in magnesium, to figure out how to safely break down hazardous chemicals, and even to fine-tune the data used in huge industrial plants. In all these totally different fields, it's the same fundamental calculation that's driving progress.
So if you take one thing away from all of this, let it be this. The real power of thermochemical equilibrium isn't about looking back, it's about looking forward. It's not just about understanding what happened in a reaction that's already over. It's about being able to predict and, more importantly, design the outcomes of reactions that haven't even happened yet. That's what makes it an indispensable tool for engineers.
When you get right down to it, the ability to calculate thermochemical equilibrium really is a cornerstone of modern engineering, material science, and chemistry. It's one of those fundamental tools that has made so many of the technological advances we rely on every single day possible.
So, we have this amazing tool that tells us a reaction's final destination with incredible precision. But here's a thought to leave you with. What if we could not only predict the endpoint, but actually control the journey to get there? Imagine being able to steer a chemical reaction, to force it down a certain path to create specific things we want, or to avoid making harmful byproducts. Well, that's the next frontier.